Hey guys, so today we're going to see a hard problem. It is a recover binary search tree problem number 99 in LeetCode. Actually, it's a pretty easy problem, so let's look at the description. Two elements of a binary search tree are swapped by mistake. Recover the tree without changing its structure. Okay, so if you look at example 1, 3, and 2, you see 1 is there, and to the left of 1 you have 3, which is a violation, and to the right of 3 you have another violation. So 3 is actually greater than 2, right? And 2 is basically less than 3, and 2 is lying on its right side. So basically you have to correct this, and once you recover this, what you will get is 3, 1 and 2. So basically you are swapping 1 and 3, and then the structure remains correct. So let's look at example 2. So 3, 1, 4, null, and 2. So you have 3, 1, right? 1 is less than 3, so this is valid. On the right, you see 4 is actually greater than 3, which is valid. But then 4 has 2, and 2 is actually lesser than 3. So all the elements in the right should be greater than 3, right? So 2 is lesser than 3. So in this case, we should actually swap 2 and 3, so that when 2 comes here, 1 is obviously will be less, and everything to the right of 2 will be greater than it. Okay, so we have to basically swap 2 and 3. So follow-up says a solution using WOF and space is pretty straightforward. Can you devise a constant space solution? Yeah, of course we can do it. If you remember the problem to find a valid binary search tree. Okay, so if you remember, we actually go and see it on the left to see whether there are any violations. And then if there are no violations, then we keep track of a predecessor value, which will basically keep track of what is the predecessor node. And whenever we see a predecessor value which is violating the binary search tree property, when I say it's violating, whenever we see a predecessor value which is greater than the current root's value, then we flag that the binary search tree is not valid. Okay, so in this case, because in order traversal of a binary search tree always produces the sorted order. So for example, if you see this tree 1, 3, 2, right? So let's move to the left hand side. So once you you go and call recursively the function on left, so which is 3, right? And by the time you reach 3, it doesn't have a left, so you will assign predecessor as 3. Okay, and then you will call recursively the function on 2, and when you call it, 2 does not have a left, so it will return. And now we have a predecessor, and predecessor's value is greater than 2, so we have found a violation in this subtree. Okay, then we will flag that particular tree as not a valid binary search tree. Yeah, the same approach we can use it here, but instead of having one particular variable to check for, we need to have two variables to basically keep track of what are the two values that are violating the binary search tree property. So this is a simple recursive in-order traversal. Okay, and when you use a simple recursive in-order traversal, space is obviously going to be whatever is occupied in the recursion stack. So at the max, it's going to be O of h, right? So so that solution is definitely constant space solution. Okay. So what we're going to do is we're just going to have a recursive function, find correct two nodes. Okay. Let this be the recursive function, and I'm going to say root. And once we find that, we will swap those two values. So we need to have some double variables to keep track of those. So what I'm going to do is I'm going to say no tree node of predecessor. This is for identifying violations. So this is going to be null, and then we are going to have tree node first incorrect node, and I will initialize it to null, and tree node second incorrect node equals null. Okay. So once we have gone inside this function, we will be able to figure out the two incorrect nodes. And so what we can do is we can have a swap function which will basically swap these two incorrect nodes. So we have to just pass in these two nodes. Okay, so let this be private functions. So what I'm going to do is let's quickly implement the private one, right? Because the private method is very easy to implement. Swap function, we'll do that swap function first. So tree node first, and then you've got tree node second. Basically, let's swap the values. So let's say int temp is equal to first dot val. Okay, and so we start first dot val. So first dot val is equal to second dot val. We'll overwrite first dot val with second dot val, and then second dot val is equal to temp. Okay, so we've swapped. Now let's go for the recursion. Okay, so this is also going to be a private void, and nodes, and here you're passing in a tree node. Okay, and this is root. So if let's do the null check. So root is equal to null. We're going to return. We can't do anything. Will return. So void function, so will return. Now we call this function for a left subtree to identify whether there are any evaluations in the left subtree. This is how in order operates, right? And finally we will also call the right subtree. So before that, what we will do is if predecessor, right, initially when you come to 3, right, or when you call left and when you come to 3, predecessor will be null. So if predecessor is null, so if this is like predecessor is not null, predecessor is not equal to null, and we'll do that condition. So if this is not there, okay, if predecessor is null, actually if it is not equal to null, and if predecessor is null, then in this case we should assign predecessor, right? So predecessor will be the current node when there is no predecessor. And then once we do this, we can just go ahead and call the function recursively for our right subtree. So root dot right. Okay, and now if predecessor is not null, and if predecessor dot val, right, if this is greater than root dot vals, right, in this case we've got a violation. Okay, and if this is a violation of the first, let's assign y the second incorrect node. Okay, so in this case the second incorrect node is going to be our root, because the first incorrect node is going to be the predecessor. Now let's see if we have already encountered the first incorrect node. The first incorrect node has already been assigned. If this is equal to null, then in this case what you will do is you will assign first incorrect node is equal to predecessor. Okay, so if not, we can actually return, because we have figured out both the first incorrect node and second incorrect node. So time to figure out and swap those two nodes. Okay, so for this example 132, let's run through this example. If you look at valid, trying to find out valid binary search tree approach, it is, basically we're using the same thing. It will also have if predecessor is not equal to null. I don't know why I have this exclamation mark in front of predecessor. So if predecessor is not equal to null and predecessor.val is greater than root val, then it's a violation. So we'll actually return from here saying that it's not a binary search tree. We are basically using the same approach here, and we are just having a two variables which basically keep track of the incorrect nodes which need to be swapped. Okay, so let's take this example. So 1, 3, null, null, and 2. Okay, so what we'll do is we'll call this function with root. So which is root is actually what? 1, right? If I find an incorrect node of 1, you will call this, and then you see that you have to call it with roots left, because 1 is not null. So we will call the left subtree, and if you say left subtree is 3, right? So we'll call it with 3. Okay, and with 3 is not null, so we will recursively call it with its left node, which is actually null. So 3 is left will immediately return because root is equal to null, so it will return. Yeah, so now left of 3 has returned. Yes, so left of 3 has returned. So now predecessor is null. So predecessor is not null, then we can go inside this block, but predecessor is null. So what we'll do is go ahead and assign predecessor. Predecessor is nothing, the current node, which is 3. And then we'll call find and correct nodes of root dot right. So 3's right is what? 2. Okay. So we call find and correct node of 2. Okay, and now if you see, it doesn't have a left, so its left is returned. Okay, and now predecessor is not null, so we have encountered this condition. And see if predecessor's value is greater than root's value. Of course it is. 3 is greater than 2, right? So 3 is greater than, yeah. So in this case we are going to assign the second incorrect node. So the second incorrect node is going to be the current node, which is 2. Okay, and we are seeing whether first incorrect node is null. Yes, of course it is null. So we'll go ahead and assign first incorrect node as 3. Okay, so now we have come to this position, and once we do this, we come out of it, and now we assign predecessor is equal to 2 because we have to assign predecessor as the current node. So predecessor is 1. Okay, so we have come out of this particular thing, and now we are at 3. We have processed this, so we are at 1 again. Okay, and at 1 we see we have returned from our left completely, and now we have to see if predecessor is not null. Of course predecessor is not null, and predecessor is what? It is 2, which is actually greater than root's value, right? So left is returned. Left 1, that recursion has already returned, and so now we are in this block for 1. Now predecessor is not null, and predecessor is 2, and 2 is greater than 1. Okay, and so second incorrect node is going to be the current node, which is 1. And if first incorrect node is not null, right? We have to return. What is the first incorrect node? Which is 3, right? So the first is 3. So it says we have to return because first incorrect node is not null, so we return. So once we return, what we will do is we will swap these two values, right? Once this function returns, then we will swap these two values, which means we will swap 1 and 3 values. So which means we will have 3, 1, null, null, and 2, which is the expected output tree. Yep, 3, 1, null, and 2. I hope it was clear. So let's quickly run this program. Okay, so the complexity is we're just doing a recursive in order traversal, right? Just in an order traversal, you call the left, and then if the property is violated, if the binary search tree property is violated, then you accordingly set the left and the first incorrect node and the second incorrect node, and so on. If the first incorrect node is already not null, then you are actually returning it. So it is basically WOF and complexity. And when you consider space complexity, it is just the recursion stack which accounts for space complexity, which is at the max it's going to be O of h. Okay, so let's quickly run this code. So it's accepted. Let's submit this code. And yeah, it is a successful submission. Okay, so I hope it was very clear. Please like this video. Thank you guys. Bye.